Section 4.3, Addition Rule. We have calculated many probabilities for simple events. Recall simple events cannot be further broken down. When one or more simple events are combined into an event, this is called a compound event. We have calculated a few compound events, but now we introduce a more formal way to do this. Union and OR. When we are interested in finding the probability that an event A or B has occurred, we are referring to the inclusive OR. This means we want to know the probability that A occurred, or B occurred, or both A and B occurred. There's also the exclusive OR, which means either A or B occurred, but not both. For all of our calculations, we'll be referring to the inclusive OR. So you won't have to make that decision. It's just automatically going to be the inclusive, where we're considering either A could have happened, B could have happened, or they both could have happened at the same time. The probability of an event A or B can be expressed as P of A or B. The union symbol also refers to the word OR. So an alternate notation would be P of A union B. So these two are completely interchangeable. If you see OR, it's the same thing as a union, and if you say union, it's the exact same thing as an OR. To understand how to calculate OR probabilities, let's start with a sample space that is usually familiar. Example 1. A single card is randomly selected from a standard deck of 52 cards. Face cards are the Jack, Queen, or King, not the Ace. Face cards are the ones that actually have a picture of a person on them. We're not talking about the Joker. So King, Queen, and the Jack. Sometimes we think of high cards and we throw in the Ace, so just be careful with that. A face card does not include the Ace. And we want to find the following probabilities. Before we get started on those, let's just make sure we remember all the characteristics of a standard deck of cards. We have two colors, red and black, and we have 4 suits. So our suits are hearts, and there's 13 of those. And we also have diamonds, 13 of those. And then we have 13 spades and 13 clubs. Okay, so just a reminder if you don't play with the deck of cards very often. So let's take a look at example A, or portion A. We remember we pull out one card, and we want the probability that the card is red or heart. Well, let's first look at how many cards are red. Well, there are 26 red cards, right, if we add up the hearts and the diamonds. But there are 13 hearts. Remember, to set up a probability in the numerator, we're going to have the number of outcomes that fit the event, and then the bottom is the number of possible outcomes. So for the probability of red or heart, we already know that the denominator is going to be 52 because there's 52 cards. Well, our concern though with the numerator is it 26 plus 13, or is there something else I need to take into consideration? Well, we said there's 26 red cards, but if I add 13 to that, the red hearts are being counted twice. So really there's only 26 cards, including the hearts. I don't want to count those twice because of the red cards I have hearts and diamonds, and although there are 13 hearts, I would be counting them twice. So really there's only 26 cards that are either red or heart. And with your probabilities, you want to make sure to always reduce your fractions or take it down to a decimal. It depends on the direction, so make sure you pay attention to that. So the probability of a red, that the card we pulled, that single card, is red or a heart, is 26 over 52, or 1/2. Let's take a look at B. a face card, or a spade. Well, how many face cards are there? There are 3 in each suit, the king, queen, and jack, and there's 4 suits, so there are 12 face cards. And there are 13 spades. But again, we want to ask ourselves, have the spades already been counted in the face cards? So let's write down our probability. Face card, probability of face card, or a spade. Okay, and again, we know the bottom is 52, because there's 52 possible cards we could have chosen. So the 12 face cards, well, they do include spades already. So although there are 13 spades, I don't want to double count the ones that are already face cards. So it's going to be the 12 face cards plus only 10 spades that are not face cards, because we've already counted them here. So that means we get 22, and for a reduced fraction, that's 11 over 26. Or if you're asked for a decimal, possibly to 2 decimal places, that would be 0.42. Okay, one more here. Example C. A club or a diamond. Well, kind of like what we did before, we'll list out what we have. There are 13 clubs, and there are 13 diamonds, and we're looking for the probability of a club or a diamond. Well, before we had to be careful because some cards could be counted in either the first event or the second event. Well, here, clubs are not diamonds, and diamonds are not clubs, so there's no problem with the card being counted twice. So we can go ahead and add 13 and 13 together and say 26, or 1/2, or 0.05. Okay. Well, now that we've worked on a few examples calculating OR probabilities, let's set up a formal equation. So we've kind of had to think about, well, do I count this? Is this being counted twice? And we just want to have something a little more formal when we encounter different situations. So this is the addition rule for any 2 events, A and B. So it could be with cards, it could be with coins, it could be with the probability of a patient having a certain disease or condition, it could be for anything. Let's see, so let A and B be simple events in a sample space S. The probability that the event A or B occurs is the probability of A or B. Well, think about what we did. We added what was going on with the first event, and we also were adding what was going on with the second event, but really we had to subtract off when A and B occurred at the same time. So our formula becomes P of A plus P of B minus P of A and B. So if we go back to that first example, there were 26 red cards plus 13 hearts, so you could look at that as 39, but we had to subtract off the 13 cards that were both a heart and a red card. So that took us back down to 26. The same thing here in example B. There were 12 face cards and 13 spades, so that would be 25. But we had to subtract off the 3 cards that were also spades and face cards because they were being double counted. Okay, so that's where that formula comes from. Remember, we also have the notation, set notation with the union symbol. Pretty much looks the same, so P of A union B is equal to P of A plus P of B minus P of A and we use the intersection symbol instead of and. So P of A, and I still tend to say and B, but intersect B. Okay, let's try, now that we have our formula established, let's take a look at example 2. Again, we're going to look at a standard deck of cards. And this time we want to know what is the probability that the card selected is a black card or a heart. So again, let's list out what we have. Black cards, that's going to be spades and clubs, and there are 26 cards, those. And hearts, there are 13 of those. So we're looking for the probability of a black card or a heart. And if I use my formula up above, I know that that's really the probability of a black card plus the probability of a heart minus the probability of being a black card and a heart. Well, in every case, remember the numerator is going to be that 52 because there's 52 possibilities. So if I'm interested in just the simple event of pulling, or that's really not a simple event, but the event of pulling a black card, that's 26 out of 52. The probability of pulling a heart would be the 13 hearts we know are there out of 52 possible. And then here is where I'm looking for the two attributes that happen at the same time. Well, are there any black cards that are hearts? No, because hearts by definition are red. So we get a 0 out of 52 here. And when we add our fractions, we end up with 39 over 52, which reduces to 3/4 or 0.75. So, and we kind of saw that in example C of example 1, part C rather. So here with the clubs and the diamonds, we didn't have to subtract off anything because there were no clubs that were also being counted as diamonds. And that's also what happened here with that 0. So that leads us to something called mutually exclusive events. Let A and B be simple events in a sample space S. If A and B are mutually exclusive, you'll also see the terminology disjoint, that means the same thing, then the probability that event A or B occurs is the probability of A plus the probability of B. And we don't have that minus P of A or B. And when you saw what happened to it is it went to 0. So we just don't bother to write it down. And it looks exactly the same in set notation with the union symbol. The only difference with mutually exclusive is that last part. So if we were to have that minus P of A and B, well, it really goes to 0. So we don't bother to write it if the two events are mutually exclusive. Try out one more here, example 3, and we'll keep the formula in view. Let B and C be two events such that the probability of B is equal to 0.71 and the probability of C is equal to 0.2. Determine the probability of B union C given that B and C are mutually exclusive. So having this piece of information here is really, really important. We know that they're mutually exclusive or disjoint, so we're going to use this formula up here. So that means the probability of B union C is just the probability of B plus the probability of C. So the probability of B we were told was 0.71, and the probability of C is 0.2, so that gives us a probability of 0.91. And that's it.